Okay. So in today's class, we will be talking about this HMM, that is Hidden Markov Model. In the previous class, we have already discussed what is Markov chain. So that was the foundation, and that was the important concept to understand this Hidden Markov model. So now we know what is Markov chain. So now we can proceed towards the HMM, that is Hidden Markov Model. So let's get started. So what is actually Hidden Markov Model? Let's read it. So these are the slides taken from Stanford University. So let's read it. A Markov chain is useful when we need to compute a probability for a sequence of observable events, right? When we have sequence of observable events, then we use a Markov chain, right? That is very useful. Yes or no? Because we have seen, like, if we are starting from one state and we are going to another state, now the probability to what will be the probability to reach at the next state will depend on the current state, right? So that Markov chain is very useful when we have to compute a probability for a sequence of observable events, right? In many cases, however, the events we are interested in are hidden. Now we will see some we will see few cases, and there are many cases, not just few cases, where the events are hidden. Okay, where the events are hidden. I will give you the example also, and we don't observe them directly. So those events are not directly observable, right? For example, let's say we don't normally observe part of speech tags in a text, right? Rather, we see words and must infer the tags from the word sequence. So we call the tags as hidden because they are not directly observed in the text. Clear? So this is one of the example. Now, what this hidden Markov model says, hi Manjunath. So what this hidden Markov model states, it allows us to talk about both observed events, the events which you can observe directly, like the words we see in the input, and hidden events as well, like parts of speech tags. So we can infer, basically using the probabilistic model, we can infer the hidden states as well, or hidden events as well, that we think of as usual as casual factors in our probabilistic model. And HMM is specified by the following components. So what are the components that we have? Let's see here. So as previously discussed, we have a set of states, we have a set of n states, right? What else we have? We have this initial probability distribution, if you remember in the previous class also, like from which state we are going to start, right? So probability distribution of all the states is provided to us. So that is initial probability distribution. We also know this transition probability matrix, right? If a state transition diagram or a Markov chain is given to you, basically, then using that you can write the you can build up the transition probability matrix, where you write the probability of moving from one state to the next state. Correct? So these three things we already know, but now if carefully observe, we have something new here. What is that? That is a sequence of observation likelihoods, or we call it as emission probabilities, or we call it as emission probabilities. So let me give you a simple example. Let's carefully understand it. Let's say we have two states. State S1 is there, state S2 is there. Okay. Now maybe there is some probability of for these transitions. So from state S1 to S2, then from state maybe S2 to S1, and like this. So let's say now this is, you can see clearly that this is a Markov chain, and this is a directed graph. So we have let's say some probabilities are also mentioned over here. Maybe this is, let's say, 0.8, right? And this is 0.2. Let's say this is 0.3, and let's say this is 0.7. Correct? So this is our Markov chain given to you, right? Now carefully understand this. When we talk about hidden Markov model, then in many cases what we have is we have observed state also present over here. Let's say there are two observed states we have. Okay, let's say there are two observed states. I will give you a real life example also, where you can easily understand, but just understand how the structure, how the components are there for this hidden Markov model. Okay, so this thing you all know. So we have this graph given to you, the Markov chain is given to you, but now these events S1 and S2, they are hidden events. They are hidden events. That means these events are not directly observable by the you can say by the AI agent or by the user, right? But if I talk about these two events, these are observable events. These are observable events, and from this S1, there is some probability. Let's say maybe let's say 0.8. So let's say 0.8 is the probability of this from S1 to O1, and there is one more probability from S1 to O2. Let's say it is 0.2. Okay, these are different probabilities from this one. Okay, when I talk about these probabilities, these are transition probabilities. Okay, from one state to another state, and these are hidden states. S1 and S2 are hidden states. But if I talk about O1, O2, these are observable states. Okay, so for these probabilities, these are nothing but the emission probabilities, or you can say observation likelihoods. Okay, so now similarly here also, from you can say from S2, there is some probability over here, maybe let's say 0.5, and from here to here also, let's say it is 0.5. Just for a random example I'm taking. Okay, so this is what it is talking about. So if I ask you to write the transition probability matrix, can you write it? Transition probability matrix from this given graph. So yes, we can write. We know how to write it, right? There are two nodes, S1 and S2. So let's say S1, S2. So we can write easily from S1 to S1, right? That means if you are standing over here at state S1, what is the probability that the next state will also be S1? That is 0.8. So you will simply write 0.8 here. From S1 to S2, it is 0.2. From S2 to S1, it is 0.7. And from S2 to S2, it is 0.3. So this is what? This is your transition probability matrix. But if I talk about emission probability matrix, emission probability matrix, then what is that? So from S1 to O1, what is the probability? That is 0.8. From S1 to O2, that is 0.2. From S2 to O1, that is 0.5. And from S2 to O2, that is also 0.5. So this is our emission probability matrix. Is this point clear so far to each one of you? If you have any doubt, please ask. Those who have joined just now, let me just give you a quick recap of what we have discussed so far. So we started from Markov chain, right? In the previous lecture, we have discussed what is Markov chain in very detail, right? Now we are talking about hidden Markov model. So in hidden Markov model, we have some states or events called as hidden states, and some states as we call as observable states. Okay, so this thing you already know that we have set of states, that is clear. We have transition probability matrix, that was also there in Markov chain when we discussed, right? And we have this initial probability distribution over states also, like what is the probability that you are going to start from a certain state I. So that is your initial probability distribution. So those who have attended the previous class, they know these three things for sure, right? But now we are talking about this one as well. Now what is this? This is observation, sequence of observation likelihoods. We also call it as emission probability matrix. So like this here, in this case, I have clearly shown you that these states, these two states are observable states, and this is your emission probability matrix. Any doubt, anyone so far? I will give you a very good example also, where you can easily understand what I want to convey here when I say that there are some states as hidden and there are some states which are observable. Okay, you will understand it. But before that, just let me know one thing, that is it clear what is emission probability matrix? Do you have any doubt so far? If it is clear, just give me thumbs up in the reaction so that we can proceed further. Okay, nice, fine. So when we talk about this hidden Markov model, So as you can see here, there was some influential tutorial. So that is Rabiner 1989. That was given by Jack Ferguson in 1960s. So that he introduced the idea of hidden Markov models, and he said that it should be categorized by three fundamental problems. So there are three fundamental problems. Problem one is likelihood. You will understand what it is in some time. Problem two is decoding, and problem three is learning. Before going deep into it, what is likelihood, what is decoding, what is learning, what are all these problems, we will come back to this slide again after some time. Okay, but now let's first understand the phase that is decoding. Like, we are giving the name to this particular phase just for a title purpose. You will understand why we are calling it as decoding and what is this Viterbi algorithm. You will understand in some time, but you can just skip this part. Okay, you can just skip this part, and let's start with our example. I will come to these slides again, then you will be able to relate it clearly. Okay, fine. Now let's say there is one guy, and let's say whose name is maybe Tom. Okay, so there is one guy whose name is Tom. Fine. This guy lives in a city, and there are three you can say weather that is possible. So that one is rainy, other one is cloudy, and third one is sunny. So these are the three weathers that is possible. But at any given day, there will be only one weather that is possible. Like, either it is rainy, or it is cloudy, or it is sunny. Okay, this is the thing. Now there are transition probabilities given to you. Like, for example, let me just explain you this Markov chain here. So it simply says, carefully understand this, it simply says that if it is raining today, there is 0.5, or you can say 50% of the chance, or half probability, 0.5 is the probability that it will rain tomorrow also. If it is cloudy, right, there is 0.2 probability that it will be cloudy tomorrow also. Okay, so simply, right, this is nothing but Markov chain only. So if it is sunny today, there is 0.7% of there is 0.7 probability that it will be sunny tomorrow also. Similarly, if it is raining today, then there is 0.2 probability that it will be sunny tomorrow. So like this, you can read this entire Markov chain. Yes or no, everyone? Simple, right? So these transition probabilities are given to you. Okay, now based on the weather, whether it is rainy, cloudy, or sunny, your friends you can say mood or expression is changing, right? So it depends. In cloudy, it's 0.3 instead of 0.2. 0.6, it's correct now. 0.2 plus 0.4 plus 0.4, that is 1. Fine. Okay. So now carefully understand the problem statement. Okay, so this guy Tom, he lives in a city, and this is the Markov chain given to you, transition probability is given to you. Now based on the weather, whether it is rainy, cloudy, or sunny, the mood of Tom depends on that. Okay, so this is the case. Either that guy is sad, Tom is sad, or Tom is happy. Okay, now these emission probabilities are also given to you. Okay, like this. So the transition probabilities we are representing by green arrows, just based on this diagram I'm saying. And the emission probability, just to differentiate, the emission probabilities are given in the red arrows. So what it says, let's try to understand what these emission probabilities, what is the significance of this. It simply says if it is raining, then there is 0.9%, or there is 0.9 probability that the mood of Tom will be sad. Okay, if it is raining, then it is I guess 0.1. Then probability is 0.1 that his mood will be happy. Okay, so like this you can read it. Similarly, if it is cloudy, 0.6 probability that his mood is sad or he is sad. And if it is cloudy, then 0.4 is the probability that the mood is happy. So like this you can understand. Yes or no? Is this clear or not? This entire graph. Anybody here who is having confusion in this graph, just let me know once. Simple, right? If you have attended the Markov chain lecture, then you can easily understand this. Okay, fine. Now let's continue the problem statement further. So what it is that you are living in some different city. Okay, your friend Tom is living in some different city and you are living in some different city, and you don't know, as you are not living in that particular city, so you don't know the weather of that city on a given day, whether it is raining or cloudy or sunny. You don't know, you don't have any information of that. Okay, but let's say you are connected to your friend, maybe on internet, right? Or maybe you are having a video call or maybe some audio call, something like that. So you are connected to him and you can observe the mood of your friend, whether he is happy or he is sad. That you can directly observe, but you don't know the weather of that city on a given day. Understood? So this is the scenario. So if you don't know, the weather of that, so can I say that these events or these states are hidden states? Do you agree, everyone? That whether whether is rainy or cloudy or sunny, you don't know, you don't have any information about this, right? So these events or these states are hidden states. Okay, but you can directly observe, the mood of your friend, whether he is happy or he is sad. Okay, now on the basis of his mood, can you predict what weather it will be on that day? So I hope now this problem statement is clear to you. So this hidden Markov model, it helps us, or it allows us to get the information, right, based on the observed events or observable events. So we can get the information of hidden states also, we can get the information of hidden events also. So if you come back to the definition here, so it is clearly mentioned over here, carefully see this. A hidden Markov model, HMM, allows us to talk about observed events and hidden events that we can think of as casual factors in our probabilistic model. So we can talk about observed events, we can also talk about the hidden events based on the observed events. So is this problem statement clear to all of you? Any doubt? Understood? Okay, now let's proceed. So based on this graph, so as it is clearly mentioned here, that these three states are hidden states and these three states are observed variable or observed states or observed events, you can say. Okay, now based on this graph, can I write the transition probability matrix and emission probability matrix? The answer is yes, it is quite simple. So we can do like this. So the green matrix that we have, that is nothing but our transition probability matrix. Correct? And the red matrix that we have, which is nothing but emission probability matrix. So these are the two metrics that we have and that we can form based on the graph given to you, or you can say the based on the Markov chain given to you. Clear? Now, so just for more clarification, we can add the weather also, just the indexes. Basically, it is nothing but the indexes, that this is in the order. So it is, rainy, cloudy, and sunny, and here it is sad, and here it is happy. So if I ask you a simple thing, can you tell me, based on the matrix, can you tell me what is the probability that Tom is happy given that it is cloudy? What is the probability that Tom is happy given that it is cloudy? Yes. It's 0.4, right? It's 0.4. Yes, that is correct. Carefully see here, everyone. What is the probability that Tom is happy given that it is cloudy? So carefully see this. That is nothing but 0.4. Let me ask a few questions more. What is the probability that Tom is sad given that it is sunny? It's 0.2. Is this clear to all of you? Probability that Tom is sad given that the weather is sunny. Any doubt, anyone? So are you able to read this given matrices? Let me ask one more question. What is the probability that what is the probability that the weather is sunny given that it is raining? What is the probability that tomorrow the weather is sunny given that today it is raining? It's 0.2, right? So probability that the tomorrow weather it is sunny given that it is raining, given that today it is raining. So that is 0.2. So I hope now you are able to read these matrices, right? So we have these matrices and we also call them as parameters. So they are part of parameters. So these parameters will be given to us, okay? Either through either in the matrix form or in this graph form, because using graph also you can write these matrices. I hope it is clear. Okay, so now let's understand this. Let's take one example and let's understand how it is working. So let's say this is the scenario that on 2 days your friend Tom is happy and on third day he is sad. Okay, so now if I have to find what will be the weather sequence. So like this here in this case I have directly just given you that, let's say this is the sequence that we are considering. When I say sequence, that means I'm talking about these hidden sequences, hidden states. So sunny, on the first day it is sunny, on the second day it is cloudy, and on the third day it is sunny again. So I'm just predicting, let's say that, as I told you also, the mood of your friend, right, on these 3 days. But now if I have to find the sequence or the most likely you can say most likely event of input sequence or the weather sequence, if you have to find out, then how you can do it? So let's try to understand it. Can I say if I have to find it, then I have to find the joint probability distribution of the mood of your friend. So let's say I'm denoting these set of moods by y, and the weather that we have on these 3 days. So let's say I'm denoting it by x. Can I say this, that using this I can find the probability of this particular sequence? Given the mood, I can find the probability of this particular sequence. Yes or no? So just for example, this sequence is given to you, right? Okay, but I'm saying that if I have to find the probability of this particular sequence, given that this is the mood of your friend, so we can find by using this joint probability distribution. Yes or no? Because we know joint probability distribution can answer anything. Okay, so how can we proceed further? Any idea, anyone? How can we proceed further if I have to find this probability? Ultimately, Manjunath, if I calculate the joint probability, ultimately we are going to use the conditional probability only. Okay, let me proceed. You will understand. Because why I'm saying so, because using joint probability you can answer anything. So if I'm using this joint distribution, can I say this is equivalent to this one only? Or let's understand this. Let me just write it here. Let me just add one slide here. So let's say this y is equal to, so we have these three moods. So I'm denoting it by smile, smile, and sad. Okay. For x, it is sunny, cloudy, and sunny. So sunny, cloudy, and sunny. Right. Now carefully understand, everyone. Based on this graph, can I write this joint probability distribution? It is very simple. How we can write it? I can start from here. So I can say what is the probability of the day is sunny? So I can say probability of, let me just denote it by like this. Let's say it is x1, this is x2, this is x3, and this is y1, y2, and y3. Okay, just for simplicity, I'm denoting these events. Okay. So can I say first you need to find this probability of x1? Yes or no? We can find this probability of x1. Then what? Then can I say I can find this probability? See, what is the probability of y1? So basically this the mood of your friend, that is you can say he is in happy state. So if you have to find the probability, can I say it is dependent? It is conditionally dependent on this weather also, right? It is conditionally dependent on weather. So can I say that I have to write like this, that it is going to be probability of y1 given x1. Do you understand this, everyone? Just the concept of Markov chain, nothing else. That if you have to find the probability of this, you have to consider the current state. If you have to find the probability of this next event, you have to consider the probability of the current state. So it is going to be probability of y1 given x1. Is this clear so far? Any doubt? Now let's go further. So what about this one? So here it is going to be probability of x2 given x1, because this is the next state and this is the current state. So I can say it is going to be what? Probability of x2 given x1. Then further we can go. Then it is going to be what? Probability of y2 given x2, right? Because it is conditionally dependent on this x2, right? Y2 is conditionally dependent on x2. So I can say it is going to be probability of y2 given x2 multiply. What about this x3? So it is going to be probability of x3 given x2. We are using the property of Markov chain, nothing else. x3 given x2. And the last event would be probability of y3 given x3. Probability of y3 given x3. Is this clear to all of you? So can I say this joint distribution I can write like this? This thing we have already seen in Bayesian network also, if you remember. The same thing we are using, nothing else. Any doubt, anyone? Is this clear how I'm writing this? Anybody having doubt in this? Yes, Manjunath, Chandana, Sumit, Avhas. Any doubt so far? Am I audible or not? Clear now? If conditional dependence are not there, how do we write it? See, Manjunath, it is given to us, right? It is given to us. Using this, understand this. Using these transition probability metrics and emission probability metrics, we can write these conditional probabilities. Yes or no? Can I say we know the values of these? And this will be given to you. This will be given to you. right? So this is how you are going to write it. And now you can substitute the values also. So if I ask you, what is the probability of y1 given x1? What is the probability of y1 given x1? That means what is the probability that the mood is happy given that it is sunny? So mood is happy given that it is sunny. So can I set as pointed? See, without probabilities, how you can write it? You need conditional dependencies, right? You need conditional probability. That is the problem statement, right? It is already given to you. I hope it is clear. So we know this value, we know this value, all these values. So what about this value? Probability of x1. That means probability of weather is sunny. Can anybody tell me how we can find out? Yes. In general, how do we expand? Okay. Manjunath, if I simply ask you what is probability of A comma B, just tell me this simply. This is nothing but probability of A intersection B. How do we write it? Can I say I can write like this? Probability of A given B, probability of B. So in general, we write like this, right? So we know here that it is the same thing we have done here also. We know here that A is conditional dependent on B, right? And B is not dependent on anything. So the same thing we are doing here, nothing different. Is it clear now? The same thing we are doing here. Probability of x1, then probability of y1 given x1, then probability of x2 given x1. And why we are not considering other events? For example, if I ask you, instead of this probability of, let's see this case, y2. Okay, let's talk about this one. Why we are not writing? Can anybody tell me why we are not writing this one as this probability of y2 given x2 x1? This is also correct, right? This is also correct. But why we are not writing it? Think about it. See, this class is more about, growing your analytical thinking. Because then only you will be able to understand each and everything clearly. It's not just about getting the final answer. That is not important for us. Eventually, you will be getting the final answer, the correct answer. But how we are doing it, that is very important. So if I simply ask you, instead of this, why I'm not writing this? Your answer should be very simple. Sir, Markov property. In previous class, you have explained as the Markov property that the probability of the next state only depends on the current state, not on the previous states. That is the reason why I'm writing just this one. Yes, you have to. Like based on this graph, we are writing this joint distribution. Based on this graph, we are writing this joint distribution like this. Because we should have that information, right? What is depending on previous state. Like here, we know that based on the graph we are writing, like y1 depends on x1, x2 depends on x1. So we have to consider all the possible events here. Is this clear now? Okay. Any other doubt? See, we have a lot of time. Your doubt should be clear. That is very important. I just don't want to cover, everything very quickly. If you have any doubt, please ask. Okay, fine. So now, we have written this joint distribution here. Let me just, yes, Chandana. Yes, what is your doubt? Tell me. Yes, please ask. In second, we have x2 given x1. This one you are talking about, right? X2 given x1. Yeah, here it is. Now it depends on the previous state. So x2, carefully see this. Everyone, carefully see this. X2, that means cloudy. What is the probability that the weather is cloudy given that it is sunny? Based on this, can you see this arrow from sunny to cloudy? This is how we are writing, right? So if I'm finding the probability of weather being cloudy today, or you can say tomorrow, what is the probability? What is the probability of weather being cloudy tomorrow, given that it is sunny today? So this is how we are writing this arrow. You have to focus on these arrows. Is it clear? Let me just make it less messy so that you can clearly see this everything. Okay, now I hope you can see this. Okay. Is this clear? Again, I'm repeating, if I have to write this joint distribution, so I can say what is the probability of x1 into probability of y1 given x1 into probability of x2 given x1 into probability of y2 given x2 into probability of x3 given x2 into probability of y3 given x3. I hope now it is crystal clear to all of you. So now my next question is, can anybody tell me how we can find this? The hint is in the previous lecture. Whatever we have discussed in the previous lecture, based on that you can answer. Because these conditional probabilities that we know, right? We have the transition probability matrix, we have the emission probability matrix, but what about this guy? What extra thing that you need here to find this probability of x1 or to get the value? Can I say you need that pi? That pi is going to give you initial, exactly. So we started with initial probability distribution, which is pi, right? And then we have to get the stationary distribution. Excellent, Chandana. We have to get the stationary distribution. Once we get the stationary distribution, this stationary distribution is going to be a row vector which is going to have 3 values, right? So it is this probability will represent for will be representing for raining, and this will be representing for cloudy, and this will be representing for sunny. So this is what we need. Or sometimes in the question it will be given to you directly, but sometime or otherwise basically we find it, right? We can find it, but in the exam you don't have to find it. They will give you, if they are going to use it, they will give you for sure. Okay. So what I'm saying is that you have to find, this is nothing but the stationary distribution. Stationary distribution, and we know how we can get it. That is nothing but pi of A is equal to pi. When we are getting this, what is this A? A is nothing but this transition probability matrix. So when this is true, then we can say that we have found the stationary distribution, and that will be represented by this. So what is the probability? If someone asks you what is the probability of weather being cloudy, so you can answer, this is the value. Weather being rainy, this is the value. Weather is sunny, this is the value. So we can find this value using stationary distribution. But before that, I hope it is clear how we are writing it. That I've already explained it to you, right? You can just refer this again also. Fine. So we need this thing. We need this thing. But we have to multiply a lot number of. That's what I'm saying. In the exam, you won't have to do it. Okay. They will give you. Don't worry. They will give you this row vector. If they are going to ask any question based on this, they will give you this row vector. You don't have to do it. But using Python scripts and all, you can stimulate it. You can simulate it, sorry. Yes or no? Yes, you can do that. But in the exam, from gate point of view, they will be giving you. So you don't have to worry at all. Okay. I hope you got it. Fine. So now can I say that you can find this probability now, probability of x1 being sunny? So what will be the value? Everyone, what will be the value based on this stationary distribution? Can I say it is going to be 0.509 multiply, what is the probability here? Probability of y1 being happy given x1 is sunny. So that is going to be 0.8 multiply. What about this value? X2 is cloudy and given that it is sunny. So it is going to be 0.3. And what about this y2? Probability of y2 that is happy given that it is cloudy. So it is going to be 0.4. So like this, you can substitute all the values. You can substitute all the values. Wait, just let me write all the values here and then we can see here sad and sunny. So that is going to be 0.2. Yes. In earlier class, we saw some theorem stating that all states become equally likes after n number of hopes. Isn't it applicable here? Yeah, that is a Kolmogorov theorem, right? Chapman-Kolmogorov theorem. that is a way of doing it, quickly. That is a way of finding it quickly. But that is not important for us, right? That is not important for us here. For this problem statement, we are not focusing on how we are getting this because it will be given to you. Are you getting this point? This is not our major problem here. This stationary distribution will be provided to you eventually in the question. We are discussing something different here. We are focusing on this thing. That is hidden Markov model. Okay. Yeah. So just don't mix things up. Markov chain we have discussed already in the previous class. We are using the concept of Markov chain now in this hidden Markov model. Now just try to understand what we are trying to figuring out in this Markov model. That is very important for you. In the exam, mainly question, if they are going to ask you question from Markov, that will be from, mainly it will be from Markov model only. Okay, fine. So let's proceed. So this thing, it is clear to you, right? If you multiply all these, you will be getting the joint distribution, right, for this given graph. Now the actual question arises. So we have seen just one example. Now the actual question arises, what is the most likely weather sequence for the observed mood sequence? Because you know the mood of your friend, right? Whether on this given day he is happy, on this given day he is happy, on this given day he is sad. Now, based on this observed mood sequence, what is the most likely weather sequence? If I ask you simple thing, how many weather sequences are possible? Can you tell me? How many weather sequences are possible? Total. Yes? 3. Are you sure? Yes, anyone else? How many total weather sequences are possible? Simple permutation question. How many weathers you have? 3 types of weather you have: rainy, cloudy, and sunny. Now, how many weather sequences are possible? Total. 6. How come? Repetition is not possible, Abhas? Repetition is also possible, right? 27, exactly. 27 is the answer, right? 3 into 3 into 3, that is 27. Is this clear? You have three places, right? You have three places. At one place, you can have three values possible, either rainy, cloudy, or sunny, rainy, cloudy, or sunny, rainy, cloudy, or sunny. So 3 into 3 into 3, that is 27. Is this clear? So total 27 weather sequences are possible. But now the question is, the actual question is, what is the most likely weather sequence for the observed mood sequence? How can we find the most likely weather sequence? So this is the mood sequence given to you. This what you can observe. But what about the hidden sequence of the weather? So can I say, generally, can I say that for every sequence, find the probability? For every such sequence, find the probability, whichever is going to have the maximum probability, right? That is going to be the most likely weather sequence. Yes or no? Is this clear? For every such sequence, let's say for 27 sequences we have. So for every such sequence, you can find the joint distribution, right? And whichever is giving you the maximum, probability, that is going to be the most likely weather sequence for this given mood sequence. I hope that is clear to all of you. So how we can represent it? Can I say this is what we need to find out? So just an example I have given, like let's say by simulation or by writing, basically the Python script, you have written the Python script and you found out that this is that particular sequence which is having the maximum probability. Okay, based on these mood sequences on 3 days, you can find that this is the maximum, this particular weather sequence is having the maximum probability. So this is the most likely weather sequence. Clear? By Python script you have found out. Okay, is this clear? So can I say that ultimately this is what I'm trying to find out? That means probability of x1, x is equal to x1, x2, xn. So this is x and this is y. So basically hidden states are represented by x and observed states are represented by y. So can I say ultimately I'm trying to find out this, I'm trying to maximize this, that if this is my particular sequence, given that what is the probability of this sequence given that this is my mood? Yes or no? Are you able to understand or not? See, this part is given to you. Simply this mood is given to you, right? You know the mood on all 3 days. You are trying to find out the weather sequence, most likely weather sequence. So ultimately, if I say that you have to, basically you are trying to find what? Probability of x given y. You are basically trying to find probability of x given y. And for each sequence, for each weather sequence, you are going to find out. And whichever is going to give you the maximum probability, that is going to be the most likely weather sequence. I hope now it is crystal clear what is the problem statement and what we are trying to do now. Is this clear to all of you? Any doubt, anyone? Yes, no, say something. Maximum likelihood estimation. Yes, similar to that, you can say. Basically, you can say that is the same thing that we are trying to find out. But yeah, estimation is not there. Just we are trying to finding out the maximum probability that we can have. So similar to that, but not exactly. Is this clear? So finding this thing, don't you think that this is difficult? How can you find this thing? Probability of x given y. Now, if you remember, you can use the Bayes theorem. You can use the Bayes theorem here. Bayes theorem will be used here. So finding probability of x given y will be nothing but finding probability of y given x, probability of multiplied by probability of x divided by probability of y. Yes or no? So we can use this. And we know this thing, right? We can find these things. because we have transition probability matrix, we have emission matrix, so we can find these things. So we can calculate this also. So this, can I say this is equivalent to this only? Probability of x given y is nothing but probability of y given x into probability of x given divided by probability of y. Bayes theorem, nothing else. And that you have to maximize. Okay. So can I say that this thing you can ignore, probability of y? Just trying to normalize it, so you can ignore this, right? Basically, as we know, because this is nothing but the total probability or the evidence, you can say. So this y will be same for all x, so we can just ignore this value. And finally, we will be having just the numerator. Yes or no? We will be having just the numerator. So numerator, this probability of y given x, how you can write the probability of y given x? Just now we have seen that is nothing but, we can write like this, right? That is nothing but probability of y1 given x1 multiply probability of y2 given x2. That means whatever is the next state given current state, like this we have find out, right? So you can simply write probability of y1 given x1, probability of y2 given x2, multiply up to probability of y1 given xn. How we are writing this? We are using the Markov property, nothing else. Carefully see this. If this is x, let's say this is my x1, this is my x2, this is my x3, the same thing, y1, y2, y3. So probability of y1 given x1, probability of y2 given x2, probability of y3 given x3. So can I say this is how you can find the probability of y given x? If you multiply the probability of every y given every x1. Is this clear? This maths, is this clear to all of you? Try to absorb it. If you are finding it little difficult, it is not, because you already know what is Bayes theorem and all these things. Now you also know what is this Markov property. So this won't be very difficult for you. It is easy, right? Is this clear so far, everyone? Yes, no. Manjunath, Abhas, Chandana, Sumit. See, this is how we are writing this. Can I say probability of y given x? What is probability of y given x? Just carefully understand. Now it will be clear. Manjunath, just focus carefully. This is in general we are writing. Can I say this is nothing but probability of y1 given x1? Why I'm saying so? Because probability of y1 depends on x1. Similarly, probability of y2 depends on x2, conditionally dependent. Similarly, for y3, it depends on x3. So can I say if you have to find the probability of y given x, it has to be this event multiply this event multiply this event. Yes or no? That means you have to consider every possible, mood given that what is the weather. I hope now it is clear. Yeah, next depends on the current. That is the same thing we are doing. So this is how we can find the probability of y given x. Is this clear now, Manjunath? Good. So this is how we can write. And what about this p of x? Can anybody tell me what should be this p of x? Why denominator is ignored? See, this concept I also explained you in Bayesian network. If you remember, Chandana, if you have watched that lecture, here also I talked about, right? This basically we can ignore this value because y will be same for all x. This is nothing but the total probability. Yes or no? This is nothing but the total probability. So can I say this denominator will be same for every probability? It is going to be same. So this value, basically what I'm saying is this value is not going to impact anything because this is present in every denominator. For every, you are trying to maximize, right? For you can say for one weather sequence you are finding the probability, for another weather sequence you are finding the probability. So this value will be there for all. So it is not going to make any difference. So you can ignore this. I hope now it is clear. Yes or no? Or in simple words, if I say that I have, let's say I have this number 4 by 2, I have 6 by 2, I have 8 by 2. Now I'm trying to find out the maximum. Can I say this having 2 here doesn't make any difference, right? That is the concept, nothing else. Okay, fine. What else? Yeah, so I'm talking about this P of X. Can I say this P of X? No, it is not going to be pi of X. Can I say this P of X will be nothing but, why this is not going to be this? Let me answer why this is not going to be pi of A. If I say this P of X, X is equal to X2, then can you say that it is going to be, you can just directly take the value from the from pi stationary distribution? No. Why? Because this X2 depends on X1 now. This X3 depends on X2. So can I say P of X will be nothing but P of Xi, whatever is the value Xi, given that Xi minus 1. Whatever is the next state given the current state. Yes or no? Is this point clear? Any doubt, anyone? Okay. So P of Y by X, P of Y given X, we can write like this, right? Which is nothing but the product of every P of Yi given Xi. What about P of X? P of X can be written as product of every P of Xi given Xi minus 1. Do you have any doubt in these 2 points? From the stationary distribution, you can only find what? You can only find the probability of this first event, because it is not dependent on anything. But after that, everything is dependent on something. So you cannot find it directly. It is always be conditional probability, and it is always be going to be probability of next state given current state. Okay. So this is how we can write it. Crystal clear? Abhas, is it clear to you? Shall we proceed now? Nice. Okay. So after finding this, so basically now we can substitute these values, and it is going to be a product of this and that you have to maximize. Or you can say you have to find out the probability, whichever probability is maximum, you have to find probability of what? Probability of that particular weather sequence, because this is what we are finding, right? Most likely weather sequence given the observed mood sequence. So this is how you can find it out. Clear? And after simulation, you can see that this is what you are getting. After simulation, if you write the Python script. So we have just now we have understood the maths behind it. Carefully understand this. Just now, I could have also told you directly that, you know, if you simulate it, you can find this value. But how we are finding this value? This is how you are finding this value. Is this clear? Any doubt, anyone? So let's solve it also. Just verify. Let's try to verify, because we want crystal clear understanding. Let's try to verify whether we are getting this value or not. Okay. So let's do it here. Carefully see this. Just for this, by simulation, we got to know that for this particular weather sequence, this is the most likely weather sequence, and this is the probability that we are getting. So just verifying that whether the probability that we are finding is correct or not, based on whatever maths that we have learned behind it. So can I say that we can write like this, that it is going to be sunny, cloudy, given that this is what we are trying to find, right? Given that it is, you can say happy, or smile, and sad. We are trying to find this one. Yes or no, everyone? This is what we are trying to find. Okay, now use the Bayes theorem. So if you use the Bayes theorem, so I can write like this: smile, smile, sad, given that, because it is what? It is x given y, right? So now I can write y given x, sunny, sunny, cloudy, multiply by sunny, sunny, cloudy, divided by probability of smile, smile, sad. This is simple Bayes theorem, nothing else, nothing different. Clear? Okay. So this thing we can clearly ignore. Like I told you, we can ignore the denominator. Yes. Now we are left with this one. Can I say this is nothing, this particular numerator, it is nothing but the joint probability distribution for this particular sequence of events? Yes or no? Yes or no? Because if I'm writing like this, y given x, probability of x, this is nothing but probability of y intersection x, or the joint probability. Correct? So I can write like this. Now this is nothing but probability of sad, comma. So this part is for y, and this part is for x. This is comma, okay? That is sunny, sunny, cloudy. This is what we have to find out. Now it's very simple. It's very simple. Just now we have seen how we can find out. So probability of sunny, this is nothing but again the same thing, probability of sunny, right? Or let me write it in terms of x1, x2, just to avoid any confusion. So now I can write like this: probability of x1 as sunny, the same formula, nothing else. Probability of, just I'm writing quickly, probability of y1 given x1. So I'm just writing directly. You can substitute the value, because this is nothing but y1, this is y2, this is y3, this is x1, this is x2, this is x3. So I'm not writing completely, but just the formula. Okay, probability of x2 given x1 multiply by probability of y1 given x1, okay, y2 given x2, sorry, multiply by probability of x3 given x2 multiply by probability of y3 given x3. Clear? Now just substitute the value. So probability of x1 is sunny, that is nothing but 0.509, using stationary distribution, this value, and rest all the values you can find from the matrices. So it is going to be what? y1 given x1 is nothing but 0.8, y1 given x1, yes, 0.8, this is going to be 0.7. Then we have what? y2 given x2, that is also again 0.8. Then x3 given x2, x3 given cloudy given sunny, 0.3. And then sad given cloudy, 0.6. So just calculate it, everyone. Just use the calculator and let me know what is the value that you are getting. Just do it quickly. Are you getting the same value? This 0.04105. Just do it. Yes, no? Yes. So it is verified, right? So which sequence it is going to be, that is very hard to find. Understand this thing, what I'm saying. Just carefully listen to my words. Finding the sequence, it is hard to find, right? Because like you are not going to do it for 27 sequences, and they are also not going to ask you this thing in the exam. But they may ask you that if this is the sequence, then what is going to be the probability, right? What is the probability for this weather sequence given that this is the mood of Tom? So this is how you have to find it. Are you getting it or not? This type of question can be framed, and we will see one question in the next class. I will come up with one question, and if they are going to ask you any question based on HMM, that will be of that kind only. Okay, we are going to solve that question in the next class. Is this clear so far? Do you have any doubt? So you understood what is this learning phase that we were talking about? Sorry, decoding phase, not learning phase. So now we have understood it, right? So now we can just read this thing, decoding the Viterbi algorithm. So what we are trying to do in this, so in the decoding phase, we use this type of algorithm, that is Viterbi algorithm. And what we are doing, given an input HMM, so these are the parameters are given to you. When I say parameters, that means I'm talking about the transition probability matrix, emission probability matrix, and also the stationary distribution. That is given to you. It is clearly mentioned, given to you. What else is given to you? A sequence of observations is also given to you. So like this, you can relate it now with our example. The moods of your friend Tom is given to you for all 3 days, right? But now what you have to find out, what you are trying to find out, you are trying to find the most probable sequence of states. That means this. Is this clear now? What is this decoding problem that we have? So I talked about 3 problems we have. This is the second problem, that is decoding. Is this clear to all of you? Just read it again. Given an observation sequence is given to you. Parameters are given to you, that is lambda, a comma b. Discover the best hidden state sequence. This is the problem of decoding. And how we are handling this decoding problem? We are handling using this Viterbi algorithm. Is this clear? Now things are making sense. Yes or no, everyone? If you have any doubt, please ask. Okay, so the next problem that we are going to talk about is what? That is likelihood. Now we are going to talk about this first problem, that is likelihood. Now what it says, what this likelihood says, let's read it now. Given an HMM, so input parameters are given to you, fine. What else is given to you? Observation sequence is also given to you. The same thing, observation sequence is also given to you. But what you are trying to find out, determine the likelihood of this observation sequence given the parameters. Okay, now we are not talking about what? Hidden state anymore. We are talking about determine the likelihood of this particular observation sequence given the parameters. So that is our problem 1, that is likelihood. So let's start that. Let's talk about it. Is this clear? Viterbi is clear? The decoding one, I hope crystal clear. Now we are going to talk about this likelihood computation, and that is nothing but the forward algorithm. This is very, very important. If they are going to frame question from HMM, 99% of the time it is going to be based on forward algorithm. 99% of the time. Okay, fine. So let's try to understand, and this is very, very interesting. You will also find it interesting. So let's proceed. If you try to understand this algorithm using multiple standard textbooks, you will find it hard. Multiple standard sources. But I will try to make it easy for you, super easy for you. Okay, so what is this likelihood problem? Given the input parameters and observation sequence, determine the likelihood. That means you have to find the probability of a particular observation sequence given the input parameters. So let's try to understand also through our example. Now let's say in this example only two weather states are given. Either it is rainy or it is sunny. Okay. Previously we had cloudy also, but now we, just for the understanding purpose, just to make things simple and easy, let's understand that now we have two weather states, rainy and sunny, and these are the observed states and these are the hidden states. Fine. Now what the question says, the question simply says, what is the probability of this particular observed sequence given the parameters of our HMM? Okay, understood the question, everyone? What is the probability of this particular observed sequence? That means that on first day Tom is sad, on second day also Tom is sad, on third day Tom is happy. What is the probability of this particular sequence? Now we have the input parameters, that means this A, B and your pi. Understood? So how we can do that? So basically what we are trying to find, can I say I am trying to find just this thing only? Probability of y is equal to y0. That means on first day it is y0, on second day also it is y0, and on third day it is y1. Basically you can say that this is your y0, this is your y1, this is your x0, this is your x1. So on first day it is y0, on second day also it is y0, on third day it is y1. So ultimately you are trying to find this thing only. Yes or no? Correct? Okay. So now how can we do that? So let's say for a given, let's say let's say for this particular weather sequence, am I properly audible or not? Just confirm once. Once again. Okay. What is the problem statement? The problem statement is, what is the probability of this particular observed sequence? When I say this particular observed sequence, that means on day 1 Tom is sad, on day 2 also Tom is sad, on day 3 Tom is happy. So we have to find for this particular observed sequence what is the probability, and what is given to us. These parameters are given to us. These parameters are given to us. So we are trying to find probability of observed sequence given parameters. Fine. So let's say, so can I say ultimately we are trying to find this only that on first day it is y0, that means sad, second day also it is y0, sad, on third day it is y1. So how we can find it out? So let's say, for example, let's say, can I say this, that let's say this is the weather sequence, just for the example purpose, let's say this is the weather sequence given to you. So if I have to write this thing, so can I say I can write like this that is going to be probability of x0 into the same thing that we have written, right? So if I say this is my x0, x1, x2, this is my y0, y1, y2. So can I write like this? Probability of x0 into probability of y0 given x0, probability of x1 given x0, probability of y1 given x1, probability of x2 given x1, probability of y2 given x2. Okay, just a small mistake. This should be y0 and y1 because we have just two states, right? Here also, just my bad. Okay. So this is your x1 and this is also x1. And this is y0, this is y1. Now it is correct. Because we have y0 representing the mood is sad, y1 representing the mood is happy, x0 means cloudy, raining, and x1 is sunny. So I can write like this, x0, x1, x1, y0, y0, y1. So now we can just write like this. The same thing, we have already seen how we can write like this, right? So I hope this is clear. Fine. So this thing we have seen for one weather sequence. This thing we have seen, if this is my weather sequence, then what is the probability of these moods or these observed states? Correct? But how many such sequences are possible? How many such weather sequences are possible? So the answer is simple, that you have three places and you have just two states possible. Either it is raining or it is sunny. So 2 into 2 into 2, that means 8 possible permutations are there. Is this clear to all of you? 8 possible permutations are there. So that means it is possible that maybe it is rainy, sunny. Then you have to find the probability of this mood sequence. Or maybe rainy, sunny. Then you have to find. So total 8 possible permutations will be there. I can write all those permutations for you. Let's say this: rainy, sunny, rainy, sunny, rainy, sunny, rainy, sunny, rainy, sunny. Anything left? 3, 7, right? Which one is remaining? R, S, R is missing. Yes. Is this clear? So can I say these 8 weather sequences are possible? For this weather sequence, what is the probability of this particular observed sequence? Similarly, for this weather sequence, what is the probability of this particular observed sequence? So can I say like this, you have to find, and you have to find for all these, yes or no? Are you getting it or not? Is this clear so far? So for total 8 possibilities are there. So total 8 possibilities are there. So if I have to write for all those 8, can I say this is how we are going to write? This is how we can write for all those 8 weather sequences, the probability of my given observed sequence, which is sad, happy. Is this clear to all of you so far? I'm giving you some time. Just take your time and absorb this. And let me know if you have any doubt. Problem statement is different, Manjunath. Both are different problem statement. In the first problem statement, what we were finding out? We were finding out the most likely weather sequence given the observed sequence and parameters. That is decoding. Second that we are talking about is likelihood. What is that? That means given the input parameters, what is the probability of a given of a particular observed sequence? Are you getting it now? Because I'm interested in this particular observed sequence. That Tom is sad on first day, sad on second day, happy on third day. I'm interested in this, given the parameters. So both are different. Don't get confused. It will take some time for you. After this class also, once go through again, you will understand. Then where is given weather statement? It is not given here. It is not given here. But what I'm saying is, if you are, just carefully understand what I'm saying. But if you have to find probability of this particular observed sequence, can I say these are the weather sequences possible? In all these weather sequences, there will be some probability for this observed sequence, right? I hope now you are getting. It is not given to you. But I'm saying what are the possibilities that we have for the weather sequences? These are the possibilities, right? Total 8 possibilities. That means it is possible that on first day it is raining, second day it is raining, third day it is raining. And then this is the weather, this is the observed mood sequence. There will be some probability for that. Similarly, rainy, sunny. Then there will be some probability for this particular observed sequence. So we are interested in finding the probability of this particular observed sequence. Okay. So if I'm trying to find out that means we have to consider all the weather sequences. Is this clear now? Just let me know this. Exactly. Because let's say today is simply let's understand this. Today is rainy. Today it is raining. I'm sad. Okay. Tomorrow it is sunny. Then also there will be some probability for me being sad. So like this, it is happening. So if I simply ask you, what will be the probability of me being sad? So you will consider both rainy and sunny. I hope now it is clear. Yes. So the same thing here. If this is the observed, this is the particular observed sequence we are talking about. Not every observed sequence, a particular observed sequence. Then we have to consider all the rainy, all the weather sequences. So total 8 weather sequences are possible. So can I say for all 8 weather sequences, this is how you can write that? For one, we have already seen like this. So similarly, for one weather sequence, we have seen this. For every weather sequence, I can write like this. But now if you carefully observe, there are, so how many multiplications are there? So exponential multiplications we are doing. What is n here? What is n here? N is the number of states here, number of observed sequences here. Okay. And what is t here? T is length of the sequence. So basically, just a minute. N is the number of states in the observed sequence, and t is the length of the sequence. Okay. I will clarify this. What is it is actually? I just have to confirm it again. I have also mentioned in the slides, so let's wait for it. But just understand this: the number of multiplications are exponential. Number of multiplications are exponential, so it is very huge. So what we can do to reduce it? Now, if I carefully observe, you will find that few things are common here. Carefully see this. Can I say few things you are calculating again? Similarly, just focus on this part. Can I say this part you are calculating again and again? Similarly, if I focus on this thing, these two are also same. Similarly, these two are also same. Similarly, these two parts are also same. So there are multiple repetitions. If you carefully observe, there are multiple repetitions, right? So why to do these many multiplications? Can you suggest any approach if you have some kind of repetition here or overlapping substructure? Can we use some paradigm if you have already studied about it in algorithms? Can we use any paradigm here if there are overlapping substructures? That means you are calculating the same thing again and again multiple times. So it is better to store it once, and whenever you need it again, just reuse the value. Have you heard of dynamic programming? Anyone? DP? Yes. So dynamic programming can be used here, because whenever there is overlapping substructure, then dynamic programming can be used. Okay. So let's understand how we can use this dynamic programming, and then it will be very easy for you. Okay. Carefully say this. Let's understand this. This is what I'm trying to find. Probability of y equal to y0, and y1. Okay. Carefully understand this. Can I say that I can divide this into two parts? See, y0, y1 is there because that is for this particular observed sequence we are trying to find the probability. But can I say that, just understand this thing, that there are three places, there are three possibilities, right? There are three places for the weather sequence. So one case, can I say one case is on the last day, the weather state is x0, and on the last day, the weather state is x1. Can I say that I can divide into two categories, because there are two possibilities. On the third day, the weather is x0, that means it is raining, or it is sunny. Yes or no? Let's go step by step. Can I say this? Yes, we can say this. So if we can say this, then I can divide this into two parts. So now, what about this part? And what about this part? So can I write like this, that it is nothing but alpha 3 of x0 and alpha 3 of x1? What does that mean? That means the last state. The last weather state is x0. This x0 is representing that. And here x1 is representing the last weather state is, that means on the last day, the weather state is x1. That means sunny. What about this 3? 3 means the number of the length of the sequence. So 1, 2, and 3. Right? So can I write like this, alpha 3 of x0, and here it is alpha 3 of x1. Is this clear to everyone? Do you have any doubt? Even if you don't know what is dynamic programming, still you will be able to understand it. Just tell me, is it clear so far? How we are dividing it? So we are starting from the third day. Either it is going to be x0 or it is going to be x1, right? So I can write this alpha 3 of x0, alpha 3 of x1. Can I further divide it? Yes. What about this alpha 3? Can I say, see, now you have x0 here. Here it is, y1. Here it is y0. Carefully understand. Here it is y0, right? Now, can I say, again, there can be two possibilities. Either second day, on second day it is x0, or on second day it is x1. Do you agree, everyone? Just tell me this. Can I divide like this? Think about it. Take your time. If you have any kind of doubt, please ask. Clear? Chandana, is it clear? Anabhas? Okay, nice. Very good. So can I say this scenario I can write as alpha 2 of x0 now, and this one I can write as alpha 2 of x1. Correct? Because now there are two we have considered. Okay. Similarly, I can divide this part also similar to this, alpha 2 of x0, alpha 2 of x1. Right? So I can say that this is what we are going to get now. Similarly, here also you are going to have alpha 2 of x0 and alpha 2 of x1. I hope it is clear. Can I further divide it? Yes, we can. Yes, we can. So we considered that previously it is on the last day it is x0. On the second day it is x0. Now we can have x0 here on the first day also. And here it is x0, x0, and x1. Yes or no? Like this. So this is how we can categorize this. Here it is y1, here it is y0, here it is y0, y1, y0, y0. So this thing I can write now as alpha 1 of x0. That means at the first day it is x0, and here it is alpha 1 of x1. Yes or no? So we have further divided it. Similarly, this can also be divided, this can also be divided, this can also be divided, similar to this only. Correct? So, and how we can write this alpha 3? So this alpha 3 of x0 will be equal to what? This will be equal to what? Carefully understand this. Let's try to find out. This alpha 3 of x0 will be equal to what? Can I say it will be equal to, or you can see here, it will be equal to alpha 2 of x0 multiply by what? So here, here it is going to be what? You can see here. So probability of, so like this, carefully see this. On the third date is x0 and here it is y1. On second date is x0. So can I say alpha 3 of x0 is alpha 2 of x0 multiply by x0 given x0, y1 given x0 plus alpha 2 of x1, because this we are not further dividing it, right? We are not further dividing it so far. So alpha 2 of x1 into, when I say alpha 2 of x1, that means we have assumed that here it is x1. So x0 given x1, y1 given x0. The same thing that we are doing so far. Is this clear? So this is your alpha 3 of x0, this part. This is how you can calculate it. Any doubt, anyone? If you have any doubt, please ask. Clear? Okay. If anyone is having doubt like how we are writing it, is this point actually clear to you or not? Just tell me this. How we are writing this alpha 2 of x0 multiplied by this plus alpha 2 of x1 multiplied by this. Thinking. If you carefully see, if I substitute further alpha 2 of x0, alpha 2 of x1, then further alpha 1 of x0 will be there, alpha 1 of x1 will be there. So like this, if you keep on substituting, so the sequences that you are getting, this is what you are going to get now. So it will be sum of all these. Is this clear now, Manjunath? Actually, this is what we are doing it in terms of DP. In order to avoid these many multiplications, we are trying to utilize the overlapping substructure. That means once we calculate one thing, and if we want it again, we can directly use it. We don't have to calculate it again. Ultimately, we are doing the same thing only. Okay, so this is how we are having this. Now this, if you expand this alpha 2 of x0, it will be further expanded into alpha 1 of x0 and alpha 1 of x1. I hope now you are able to relate. Similarly, this thing also, alpha 1 of x0, alpha 1 of x1. So ultimately, you are going to get all the addition of all those 8 statements. Yes or no? And similarly, for you do this. So once you are going to add these two, ultimately you are going to add these two, right? Then it will give you all those 8 statements, addition of all those 8 statements. I hope now it is clear, Chandana and Manjunath. Crystal clear now? Okay. So ultimately what we can do is alpha 2 can be further divide like this, as I told you. Similarly, this can also be divided. This can also be divided. This can also be divided. And can I say you cannot further divide alpha 1 of x0? Can you divide alpha 1 of x0 further? No, because the maximum sequence we have, the length is 3 only, right? You cannot further divide it. So can I say these are the base conditions? You know what is base conditions, everyone? That means where you have to stop, right? Where your program will stop. You will not go further. Like if you have ever written the program of factorial, so when it gets stopped, the program execution, what is the base condition for a factorial? Either n is equal to 0 or it is equal to 1, return 1. Yes or no? This is what you do. So that is the base condition. So here also you have to stop somewhere, right? So something should be your base condition. This is your base condition. Once you reach at this level, you cannot further divide it because that is not possible, right? So alpha 1 of x0 and alpha 1 of x1, these are the base conditions that you have. These are the base conditions that you have. Okay. So if these are the base conditions, what is the value of alpha 1 of x0? It is simply p of x0. into P of y0 x0, because you know this is your x0, this is y0, the first day, then you have something else, right? So it is P of x0 into P of y0 x0. Similarly, alpha 1 of x1, P of x1 into P of y0 x1. Correct? The initial point, the first day. So these are the base conditions. So this is your tree will look like. But now if you carefully observe, can you see some overlapping substructure? You will definitely find it out. Carefully see this. This alpha 1 of x0, alpha 1 of x0, can you see it multiple places? That means if I compute it once, I can reuse at other places. Yes. Similarly, if you see alpha 1 of x1, alpha 1 of x1, these are also overlapping substructure. Calculate once and then reuse at every place. Directly use the value there. Alpha 2 of x0, this is also getting repeated. So once you calculate alpha 2 of x0, then you can reuse it here. Yes. Similarly, these two are also overlapping substructure. Right? So can you see how dynamic programming can be used? So whatever overlapping substructure are there, you just compute it once, store it somewhere, and then reuse them. So, what we can do now? So can I say, now we can generalize this? Carefully say this. Now we can generalize this. Alpha t of xi. How we can write alpha t of xi? Your t can be 3, 2, 1, whatever it is. So we can write like this statement. If you are thinking how we are getting this statement, this is nothing but this thing only. Alpha t of x0. Alpha t of x0 is nothing but alpha t minus 1 of x0. So like this we have substituted here. So this is the generalized form. Clear? Okay. You can just take a look at this after the class also. You will understand. Basically just substitute, you can find out. So this is the recurrence relation. Fine. Similarly, if I have multiple, like in this scenario, in our example, we had just two states, right? Raining or sunny. But if we have many weather states, then in that case, what to do? So like this, if you have alpha 3 of x0, if you have alpha 3 of x1, similarly, maybe you can have alpha 3 of x2 also in that case. Yes or no? If you have more states, then alpha 3 of x3, alpha 3 of x4. Yes or no? So basically, ultimately, you are what you are doing. You are adding these two values. If you have more values, you are going to add them also. So it is going to be nothing but the summation of j is equal to 0 to n minus 1. This alpha t of the same thing, the same equation. You are just adding all those. You are just adding all those, the same thing. Correct? And these are the base conditions that I was talking about. So base condition we can write like this: P of x0, P of y0, x0, whatever is the value of I. And you can write like this: this P of x0 is nothing but stationary distribution. Yes or no? So you can use this pi I. Correct? Corresponding value you can use. So finally, this is what we wanted to calculate, and this is what it will be. That means alpha of, if you add all these values, all alpha values, that means alpha 3 of x0, alpha 3 of x1, alpha 3 of x2, like this. So this is what it is going to give you. Is this clear to all of you? Do you have any doubt? It should be alpha t, right? Not alpha t minus 1. It should be alpha t. Because if three states are there, 1, 2, 3, then in that case, it would be alpha t, alpha 3, starting from alpha 3. Yes, so it should be alpha t only. Fine. Is this clear, this generalization? You can just take a look at this generalization again after some time, after seeing these equations, and you will understand for sure. These are not difficult. And nobody is going to ask you these generalizations also. Okay. Fine. This is a derivation, you can say. This is the algorithm, the actual algorithm that we are using, this forward algorithm. Yeah, nobody asks. So if you see the value, so carefully see this: alpha 1 of x0, alpha 1 of x1, alpha 2 of x0, alpha 2 of x1, you can calculate alpha 3 of x0, alpha 3 of x1. So once you calculate alpha 3 of x0 and alpha 3 of x1, you can just add these two values to get the final value, which is 0.1344. So this is how we are using dynamic programming, that we are calculating this value once only. And wherever we need it, we are using it. Wherever we need it, we are using it. Is this clear? So this is the probability of that particular observation sequence, that on the first day Tom is sad, on second day also Tom is sad, on third day Tom is happy. So probability of for that particular observation sequence is this. Clear? This is your, sir, I'll explain alpha 3 of x0. Okay, let me explain you here only. This part you are saying, right? How we are getting this? Okay. Let me add one slide here. Carefully see this. We have this P of y0, y0, y1, right? So what I'm doing? So let's start with this. You understood, right? How we are dividing it. On the last day, I'm assuming that this is x0, or I can assume that this is x1. So here it is y1. Clear? And here it is also y1. Fine. So this is what? On the third day, it is x0. So I'm writing alpha 3 of x0. On the third day, it is x1. So I'm writing alpha 3 of x1. Clear now? Now, what is this alpha 3 of x0? Let's try to understand this. What is this alpha 3 of x0? Can I say alpha 3 of x0? Just focus on this. I can further divide it into alpha 2 of x0. That means on the second day also it is x0, that it is raining. Or it can be sunny on second day. So can I write this? Alpha 3 of x0, can I write like this? That it is alpha 2 of x0. What else? What else? When I'm considering alpha 2 of x0, what does that actually mean? That means on the third day, you know it is already x0, that here it is y1. But on the second day also, you are assuming that is x0. Now, based on this, we can write like this: alpha 2 of x0 multiply by what? Multiply by probability of x0 given x0. Yes. Multiply by probability of y1 given x0. Yes. This is my alpha 3 based on this second part. But what about the based on left part? But what about the right part? Right part is alpha 2 of x1. Now how we are finding the rest of the things? So here it is, on the last day we have x1, right? This is y1. And on second day, I'm assuming this is also, oh sorry, this is x0, right? This is x0 on third day, because we are just talking about the left part of alpha 3. And here on the second day, I'm assuming this is x1. So now we can find probability of x0 given x1 multiply by probability of y1 given x0. Is this clear? This is the same thing that we have written over here. Now, if you have any doubt, please ask. And in the same way, you can write for every value. Clear? Okay, so this is what is our forward algorithm. So what we are doing here, so carefully see this. Yeah, here it is mentioned. For an HMM, this hidden Markov model with n hidden states. So n is your hidden states. That is the top states, right? Hidden states. N number of states are hidden. Observation sequence of t observations. So how many observations you are considering? Like how for our example, we are considering for 3 days. So t is equal to 3 in that case. Okay. So t is the sequence of observations. That means on first day he is sad, second day he is sad, third day is sunny, third day is happy. So t is 3 here in that case, in that example. So there are how many n raised to the power t possible hidden sequences? Is this clear? This is also quite logical. Let's say sad is there, happy is there. So how many sequences are possible? How many probabilities are possible here? Possible hidden sequences. So for this one also there will be one sequence, this one also there will be one sequence, this one also there will be one sequence. Now you can have how many? It is going to be so total n hidden states are there. If let's say rainy and sunny is there, these two are, so 2 raised to the power, can I say 3? That means 8 permutations are possible. That's what we have already seen, right? Is this clear? So n raised to the power t, this is nothing but n raised to the power t possible permutations, or you can say possible hidden sequences are there. For real task where n and t are both large, when in actual task when n and t are having very high values, n raised to power t is a very large number. So we cannot compute the total observation likelihood by computing a separate observation likelihood for each hidden sequence and then summing them. Like we have seen total 8 statements and then we are adding it. That will take a lot of computation. So we use forward algorithm in that case. And what we do in forward algorithm, we use the dynamic programming algorithm or paradigm. So instead of using such an extremely exponential algorithm where it is taking n raised to the power t order of multiplications, we use an efficient order of n square t algorithm, which is nothing but the polynomial called the forward algorithm. And how we are doing it? The forward algorithm is a kind of dynamic programming algorithm. That is an algorithm that uses a table to store intermediate values as it builds up the probability of the observed sequence. So it is going to have a table and it is going to store the values there. So wherever you need the same value, you are not going to recompute it. You are just going to use the value. The forward algorithm computes the observation probability by summing over the probabilities of all possible hidden state path, that means alpha 3 of x0 plus alpha 3 of x1, that could generate the observation sequence. That is your forward algorithm. Is this clear to all of you? Crystal clear? Do you have any doubt? If you have any doubt, please ask. Okay. The third one, that is not, I would say, in the GATE syllabus, they are not going to ask you, but just you should understand what it is. We are not going to see anything in this. Just one slide is there. HMM training, the third problem, right? We had first problem, likelihood, that is forward algorithm. We use forward algorithm for that. Second one is decoding, where we use Viterbi algorithm. Viterbi algorithm, yes. And for training, we use forward backward algorithm, which we also call it as Baum-Welch algorithm. And that is a special case of expectation maximization, EM algorithm, which you study in ML. Okay, I don't know whether it is there in your syllabus or not. I think it is there, right? EM algorithm, expectation maximization. Fine. So here what we do, just understand the problem statement. That's it. Nothing else you need to focus on. So we turn to the third problem of HMMs. So these are the 3 problems. Learning the parameters. Now you have seen in first 2, that is decoding and likelihood, parameters are always given to you. Yes or no? That means the probabilities, transition probability matrix, emission probability matrix is always given to you. But what we don't know it, then we try to learn it. Okay. So learn the parameters of HMM, that is the A and B matrices. So this is the learning problem. Given an observation sequence, now observation sequence is given to you. What else? Hidden states are also given to you and the set of possible states. So these 2 things are given to you. Now you are trying to find, or you are trying to learn the HMM parameters A and B. That is the learning problem. And for that purpose, we uses this forward backward algorithm, which we also call it as Baum-Welch EM algorithm. Is this clear? That's all you need to know about this one. Is this clear? Okay. Just give it a read to this paragraph. You will understand. It is simply learning, right? Forward backward algorithm. That means again and again, you are trying to get closer to, so iterative, there will be multiple steps. And again, you are trying to you are trying to get the better estimate of what should be the parameters. And finally, when you reach at a certain point, so again, this, it is same as, you know, the gradient descent or nothing. That is the same thing. Okay. In the neural network also, you try to stabilize the weights, right? So that is the same thing here. Similar to that, I would say. Clear? So what is the summary? The final summary of today's lecture. This chapter introduced the hidden Markov model for probabilistic sequence classification. Hidden Markov models are a way of relating a sequence of observations to a sequence of hidden classes or hidden states that explain the observations. Second thing, the process of discovering the sequence of hidden states given the sequence of observations, when observation sequence are given to you, is decoding or inference, and the Viterbi algorithm is commonly used for decoding, that we have already seen, the first problem that we have seen. And second one is your parameters of HMM are basically when we try to learn the parameters, both can be trained with Baum-Welch and forward-backward algorithm. And third thing that we have seen, which is forward algorithm, that is likelihood. So from this particular topic, forward algorithm is important. Some questions can be framed on that, and Viterbi algorithm that I have covered through one example, that is also one question can be framed. And it may be possible that 1 mark theoretical question can also be asked. Okay, clear? So you should know all these 3 problem statements clearly, what it is talking about, right? If I say forward algorithm, where we are using it. If I say Viterbi algorithm, where we are using it. If I say forward backward algorithm or Baum-Welch algorithm or EM algorithm, where we are using it. So learning, decoding, and likelihood, you should be clear with that. This is important from this point. One question I will be covering tomorrow, and I will also be starting with